Hello, everyone. My name is Jakob Nyberg. I'm from KTH in Stockholm, Sweden. And I'm going to talk about my work on reinforcement learning and cyber attack simulations. Next slide, please. This is part of the project called Sentience, which is funded by the Swedish Civil Contingency Agency. And it has it's been going on for 2 years, roughly, and it has the long-term, quite lofty goal to develop a semi-autonomous security operations center, SOC, if you will. And the idea behind that term is to use machine learning, modern developments in machine learning, to filter and analyze the current threat situation, and also to be able to plan ahead and produce policies for defense. Next, please. But the key point here is that we don't want to replace humans in this process. This should serve as a resource, a complement to human capability. The current approach that we've taken is to look at the problem of network intrusion response. And we want to automate response using reinforcement learning. And we don't need to go too much into this, but reinforcement learning is the subfield of machine learning dealing with actions, taking actions. And you learn through trial and error and interacting with your system. The problem there is that you need quite a lot of data and you need quite a lot of interaction. And with a computer network where actions can take several minutes to perform, it becomes more practical to train in simulation. Next, please. But then use the generalization capabilities of neural networks to be able to evaluate then your system in a real network. Next, please. So then the question becomes, how do we simulate a cyber attack? And there are a lot of candidates for this problem, and this is ours. We use a modeling language developed at KTH called the meta-attack language. And using that, you can create attack graphs, somewhat similar to what we saw before. And these serve as the sort of basis of the attack simulation, where an attacker will performs attacks from the attack graph, and we assume, so you can go to the next slide. So that was a static model, and then you have to take this and create some sort of episode training structure around it. And then we assume that we have an attacker and a defender agent. The attacker will perform steps from the attack graph. This raises alerts. Then a defender agent will read those alerts and activate predefined defenses. That then you don't need to go. Yeah, go back one slide. So the defenses will stop the attacker. So the goal for the attacker is to grab certain targets. The goal for the defender is to stop the attacker. And a key point here is, how do you, a bit of related to the quantitative analysis here, something that we've had to think a lot about is how, with reinforcement learning, you need to define a reward function, something that measures how well your agent is performing during training. And this is actually something that is quite tricky, because how do you validate this quantitatively? What we do currently is that you get minus points essentially if you let the attacker grab flags, but you also get, if that was the only optimization goal, then it would be quite easy just to enable all your defenses immediately. So what we do is we add a secondary optimization goal of trying to reduce the amount of downtime that these actions caused. So now you can go to the next slide. So the assumption here, when we do this, when we build this attack graph and we simulate on top of an attack graph, is that we assume that we have some system that can map actual data in a computer network to nodes in this attack graph. And this is quite a strong assumption because we need some system to do that. So what we do now is that we assume that some system is in place, could be a machine learning system, could be just some static rules, but we do assume that it can be faulty. And the question then is, how much faults can you accept before your reinforcement learning agent can't operate anymore? So that was something that we wanted to test in the experiments that we come to later. Next slide, please. So this is not in the paper, but I thought I would bring it up just to show that we have some anchor to reality. What we're working on right now is taking this reinforcement learning agent out of the simulation and evaluating it in an actual, albeit emulated, cyber environment. And this is provided to us by the Swedish Defense Research Agency, FOI, and they have a cyber range where they do a lot of blue team exercises. They also have an attacker, a red team automation agent that they call LORE. Next slide, please. But we're still in the simulation stage, so we did some experiments within the simulation to evaluate some of the things that we were interested in. And these were, for example, testing against different attacker policies. We wanted to test the sort of limits of the false positives and false negatives that this mapping process produces. And also what happens if you just scale up the attack graph. Next slide, please. So this was a result that we obtained when we we basically tested all combinations of false alerts or false negatives and false positives, and then we measure how many flags get taken, how much reward the agent gets. All the rewards are negative here because there's nothing. You only get negative rewards because the only thing you can do is shut things off, and then you get a negative reward. But this is for a heuristic policy that we implemented as a baseline. It's basically just an if this then that rule, such as you would have in like a host-based idea system. And it works really well when you have no noise in your alerts. Then it starts planing out once you have a lot of false positives because it will trigger prematurely. And then it doesn't work well at all when you have a lot of false negatives. Basically, you're missing your alerts because it will never trigger. So that's why there's a big spike here of like the attacker taking flags because system never triggers. Next slide, please. So the reinforcement learning policy actually learns to sort of counteract some of these things. It's still plain like flattens out when the false positive rate gets too high because there's nothing to do. There's just noise. And the reason it can do this is because it figures out that the if this then that rule will only trigger on one specific step, whereas the reinforcement learning agent has more information provided to it, so it can choose to filter out, choose to use other information even if there are false alerts. Next slide, please. This is a slightly confusing image, just showing that this is what we got when we you train with one attacker policy and then evaluate with another. And what we saw here was that certain opponents were better than others. So an attacker, when you trained against an attacker that just used a breadth first strategy, the defender performed really well against it, but it performed really poorly against everything else. And there's probably some game theorist in here that can tell me that, well, you should always do your policy against the most exploitative opponent, and there's probably some basis here in that there are certain opponents that are better to train against than others. Next slide, please. We also saw that there's an issue here with when we scale it up, performance goes down, and this is partly because of optimization reasons, because now we just use a neural network to train the policy function. And as we scale up the attack graph, we also have to scale up the neural network, meaning that your hyperparameters become less optimal and therefore performance goes down. So this is something that we're working on right now to perhaps incorporate graph neural networks to to not have to increase the number of parameters in your model as the attack graph grows bigger. That was basically everything. Now I'm open for questions. So if you're not an academic and you think that this whole thing seems very removed from reality, feel free to say so, because I'm really interested in hearing what people who are not AI people have to say about this.
I'm curious to what degree you're looking to automate this process. You said that this is more to augment the tier 1, tier 2, tier 3 analysts, but it sounds somewhat along the lines of what the Cyber Grand Challenge was back at DEF CON a few years ago, where it's a fully automated system that
right now it is, because we have not sort of incorporated real humans in this loop yet, and that becomes we are sort of working on this, how to develop this in a sort of user interface. It becomes a user interface problem also, because how do we present this information to the SOC analysts? And you could also argue that if you have this attack graph, for example, what's the benefit to just showing the attack graph? You don't suggesting actions, but might be a smaller part of this.
So I had a question. One of the challenges as an academic is scale. And you, on your last slide, sort of, pointed out that one of the challenges is as you scale, your results change. Earlier, we heard the scale, in the industry you talk about is 300,000.
Yeah.
And I just wanted to understand what scale you used, and do you have a sense of your results are valid till what scale?
So the thing now is that these operate on an attack graph level. And the thing with the attack graphs is that they become very big, very fast. But what we would want is to maybe move on to an instance model level where you have hosts and networks. So on the attack graph level, it doesn't work. Not very big at the moment. But that is partly because we're ingesting the whole graph all the time. And you don't really want to do that, regardless if it's an instance model or an attack graph. So that is something that needs work right now.
Have you thought any about the utility for using this for incident response in terms of specific cases where you know what an attacker has? I guess in essence, you're trying to figure out a specific attacker, and then using that to model or understand what the lengths of the attacks are. Because I see great utility from that perspective, but I didn't know if you thought, are you thinking just micro specific, or are you thinking macro? Let's explain what all attackers do with these attack graphs. I guess I'm trying to think about the utility.
So this is on the meta attack language has that's the abstract language, and then there are specific domain-specific languages.
Okay.
So there are vehicle lang, for example. There's core lang, which focus on the AVS infrastructure. So that's a question I would defer to them, perhaps.
Gotcha. Okay.
But then on my side, it would be the attacker behavior, perhaps, and how does an attacker sort of choose these attack steps from the attack graph?
Yep, that's what. Okay.
And modeling that behavior is sort of an open question right now. We are maybe looking at, you can flip this and start saying that, if we can train a reinforcement learning defender, maybe we can train a reinforcement learning attacker, which is a more dark side of this. But it is an open question.
I had a question about your choice of using reinforcement learning.
Yes.
So I'm looking into this problem using reinforcement learning for red agents and blue agents. So you mentioned that the attack graph can get very big very quickly if there are a lot of states in the network, and you're trying to manage each of those states. And then you said you're using neural networks to for this purpose. So why did you not choose DQNs? Why did you stick to reinforcement learning, or is that what you're using as a generic term in your paper?
So you're saying that we should use deep Q or deep Q networks?
Yes, because you will be able to keep track of. I'm curious. I've not used DQNs.
Or do you mean graph neural networks or deep Q learning. Or,
Deep Q learning.
well, you would not. So
they are used for reinforcement.
yeah. So now we're using PPO, but we would have the same problem in the current implementation if we were using deep Q learning, because with deep Q learning you would still use a fixed size neural network to predict the Q value.
Mm-hmm.
But I think what we need to do here, if we're sticking to this graph data domain, what we probably want to do is use what's called a graph neural network.
Mm-hmm.
And that's similar to how if we have an image, a convolutional neural network doesn't increase in size. You can take any size of image with a convolutional neural network, but you're not changing the parameters of your model. It sort of sweeps across the image. And the same is true for a graph neural network, that you're sort of sweeping across the graph, or you're doing message passing, essentially. So you're doing message passing in order to, even if your graph becomes bigger, your network, the number of parameters in your network stays the same. And that makes it much more easier both to optimize it, but also to generalize, because that's what we want to do when we do machine learning or deep learning specifically, that if we can perfectly simulate an attack, then we don't even need machine learning for that. Like, you can just solve the Markov decision process using a solver. But what we want to do is we want to exploit the fact that neural networks can generalize. And right now, the architecture that we're using is pretty bad in the sense that it can't generalize across graph structures. And what you would want to do is to be able to train on a bunch of different architectures and then learn the semantics, perhaps, of the system, and then transfer that into your real network. That requires an architecture that it is permutation invariant to the structure of your network. That is a bit of an open challenge at the moment.
Okay.